Hello and welcome to the second edition of Zoom University's Recitations Online. Today we'll be talking about a first look at electrodynamics. Recall that electrostatics means that electric fields stay stationary with respect to time. Magnetic fields, similarly, in magnetostatics, stay stationary with respect to time. Dynamics means that they change. There is good reason for suspicion. First, the magnetic field is an electric field from a different frame of reference. As you may recall from a video we watched in a previous recitation, if we were a positively charged cat, and we were moving in the reference frame of the electrons, i.e. we were moving at the speed of the current, we would notice there would be contractions of the protons, and then we would experience an electric field from a positively charged wire, whereas in our own reference frame, where the electrons are moving and we're not, what we see is a neutral wire, yet there is still a force on the cat, of course. The physics is still the same no matter which observer you are. Instead, we attribute this to the so-called magnetic field. Therefore, an electric field and a magnetic field are not entirely distinct. An electric current, additionally, comes from an electric or changing charge. So, the way in which we can phrase this question is, could a changing electric field or magnetic field induce a magnetic field or an electric field? The answer turns out to be yes. Let us begin by watching this animation in which there is an experiment that is being conducted. A magnet is being put through a solenoid, and what this will do is change the magnetic field. As you can see in the voltmeter, there is a potential difference across these wires, which causes a current, and the current goes through the light bulb and lights the light bulb. If we add a second coil, we will notice that a similar effect occurs, even with less coils. There is still going to be a similar effect. And if we flip the bar magnet, as you will see now, there will be a large flash due to a strong change in the magnetic field. Therefore, the potential difference seems to have to do a lot with how the magnetic field is changing. Now let's discuss this in a little bit more detail. There are a series of experiments that can show how this can be done and what we can attribute this to. First, let's take a bar magnet, shown in the gray box, and a loop circuit, shown as the regular circuit with the current going through it. And let's examine what happens under different setups. First, let's take the loop and move it to the right, and keeping the magnet stationary. There will be an induced current in the loop. Let's move the magnet to the left, holding the loop still, current still flows. And finally, let's keep both of them still, but strengthen up our magnet, make it stronger. Current still flows. Therefore, and doing various other experiments to show how it doesn't change, we know that a strengthening magnetic field and a greater area creates a stronger current. We can therefore say that the potential difference, which we will call the electromotive force, which is a bad name since it's not a force, it's a potential difference, is proportional to what we call the change in the flux, where the flux is the integral of the magnetic field over the area. This is called Faraday's law. The electromotive force is called script E, and it's equal to minus the time derivative of the flux. The minus sign is attributed to something we call Lenz's law, and we will discuss this now. But I want to take a side note to note the history. Michael Faraday discovered this law in and around 1831, and at first it was not clear exactly what the implications would be, but it turns out it was one of the most massive achievements in terms of human technology. Because of this, we can use things called AC circuits, which are significantly more powerful than DC circuits. As a fun side note, Thomas Edison originally worked on DC circuits, whereas his student Nikola Tesla worked on AC circuits. Thomas Edison feared that AC circuits would not only run him out of business, but they were also extremely dangerous, and therefore he invented the electric chair to demonstrate how dangerous this could be. Of course, with short-sightedness, everyone saw this as a reason why electricity was something to be scared of entirely. He also invented a death machine as a result of his jealousy. Lenz's law is the minus sign in this equation. The key point is that nature hates changes in the magnetic flux. It does not want to have the magnetic flux change, and therefore, it creates a current that opposes the magnetic flux. Recall that a current generates a magnetic flux through the material, as we saw in the solenoid and the loop in the previous recitation. Therefore, if a changing magnetic field causes a change in the flux, the circuit will respond by generating a current that opposes this. So, The steps to finding the direction of a current in a Lenz's law problem, or a Faraday's law problem, is to first consider the flux before and after the change. Then, we will use the right-hand rule to find the current direction that generates a flux in the opposite direction of this change. In the below example, I show a couple of situations in which this would occur. Let's look at it on the top first. What we're doing is we're putting a bar magnet into the solenoid. In that case, what we're doing is we're going to create even more field lines that are going to the left. And in doing so, that means that we need to respond to this. So we need to create a current that produces field lines going to the right. Therefore, we have a current going down, as shown, and you can verify via the right-hand rule. We will do something similar on the top right, where we take it out. And so what we're doing is we are removing field lines that are going to the right, meaning that the net change is more field lines going to the left. Therefore, we again need a current that produces more field lines going to the right. Therefore, we have a current that is going down as such, which again you can verify via the right-hand rule. Then, what we have on the bottom left is we are taking out a north pole, meaning fewer field lines are going to the left, meaning there is a change going to the right. The induced field must oppose this, and so it is going to the left. And so by the right-hand rule, we generate a current going up on this side. And similar story for the bottom right, we take a south pole out, meaning that there are fewer field lines going to the right, and therefore, we're moving the south pole in, meaning there are more field lines going to the right, my apologies. And this means that we need to create an induced current going to the left. Let us examine this in terms of more concrete examples. First, we consider this setup, in which you have a bent wire, shown here in the thin black, with points PQ and a distance L between the ends, and a metal bar that is put over here, moving at a speed V, and a magnetic field going into the page. The resistance per unit length within this wire is lambda. The current in the circuit is moving counterclockwise. The reason you can tell this is because first we have to observe the changes. In the beginning, you can count 6 field lines going in. Later, this will grow and there will be more field lines going in. So the field stays constant, but the area grows, meaning that there is a greater flux going into the page. To generate a flux going out of the page, you can verify by the right-hand rule that you have to have field lines coming out of the page, and so the circuit should go counterclockwise. The electromotive force is computed as follows. You have minus d dt. Then, if you didn't use Lenz's law, you could also just plug in the signs correctly. We have a field going into the page. That is minus bz hat. The area vector is going to be x, which is the distance from this side to the bar, times L, which is this. With this vector going out of the page, since they are anti-aligned, there is an overall minus sign between them. When you differentiate, b and L are constant, and dx dt is v, meaning that the electromotive force is b times the velocity times the length. The resistance is a function of time as well. Recall that we were given a resistance per unit length, lambda, and so what we need to do is multiply lambda times the total length of the wire in consideration. This is x plus L plus x, and this bar is resistanceless. Therefore, we do not count it. And so the resistance is lambda times L plus 2x, or since x is the velocity times time, lambda times L plus 2 Vt. The electromotive force divided by the resistance gives you the induced current, which is BVL divided by lambda L plus 2 Vt. The steps to solving these problems are therefore 1 to find the magnetic flux via either Ampere's law or it is a given constant, and integrate over the area. You take the derivative and use velocity if needed, and then find the resistance so that you can divide out the resistance to find the induced current. As a second example, which is more relevant for your homework, a light bulb has resistance R, and there is a current going through an external wire of I equals I naught minus KT, where K is a constant and I naught is a constant. Therefore, the current is decreasing. As you recall from the previous recitation, you can use the right-hand rule to find that in here, the current is coming out of, or the magnetic flux is coming out of the page. Since the current is decreasing, then what you find is that the magnetic flux coming out of the page decreases, and so the net change goes into the page. To oppose this, you need to generate a flux going out of the page. The current that achieves this inside this loop is a counterclockwise current. So the current in here, you have I induced going counterclockwise as such. The magnetic field via Ampere's law from this current is mu naught I over 2 pi r. Now we can compute the electromotive force. The infinitesimal area is BdR. The reason is because what you have is B here, and then in the direction of change, which is in this direction, you can have a dr going this way, since B depends on r, but it doesn't depend on any lateral direction as such. So the infinitesimal area is B times a little change here, and you're going to integrate from d to d plus a. And this is shown in this integral. You integrate from d to d plus a, the magnetic field, and the infinitesimal area is BdR. We can compute that integral, and what you'll find is that you get an ln. dr over r is ln of d plus a divided by d. Then, I substitute for I naught minus kt. Since everything here is constant, d dt doesn't affect the ln, but it'll affect this quantity here, and it will leave behind a minus k, which will cancel out this minus, verifying what we found before. A positive current will move in the counterclockwise direction. Additionally, you can divide by the resistance of the light bulb in order to find the induced current. And if you wanted to find the power going through the light bulb, you would need to recall the formula V squared over R, which is the given power. So you would need to square this and divide it by R to find the power. What about electric fields? Yes, we can go in the reverse direction. A changing electric field does indeed induce a magnetic field. Faraday's law tells us that a changing magnetic field induces an electric field in the wire, which causes a current. In this situation, what we have is a changing electric field. The common example is attributed to Richard Feynman, and it's a capacitor. What you have is a current, and it builds up charge here, and it causes a change in the electric field, since more charge means more current. And what that does is it's going to cause a buildup of negative charge here, which causes the current to continue moving this way. This can be thought of as having the current continuing through the entire capacitor. But we know that a current induces a magnetic field. So if the capacitor is stationary, then we can tell that there is no change in the electric field and it cannot be thought of as a current. But when it is changing, all of a sudden, there is a type of current that is going on. And this current causes a magnetic field. But we will not have to worry about this too much. Faraday's law is of significant more importance because this type of effect only occurs at a scale of 1 over the speed of light squared, which goes as 10 to the minus 17, almost. And that is an extremely small effect in SI units, of course. The next topic I want to talk about is inductors. These are the analog to capacitors. You can form an inductance between different loops in the same way we found capacitance between different conductors. But more commonly, you want to deal with the self-inductance of an object, which can be found by dividing out the current from the flux times the number of loops that are present. This is important when we deal with circuits next week because the voltage drop due to an inductor is minus the self-inductance times the change in the current. As you will note, this is very similar to 1 Ohm's law and also to the capacitor rule. For capacitors, we had 1 over C times Q. The charge is what caused the potential difference between capacitor plates, and the capacitance describe the geometry of the material in question, and it is something that is given in the circuit. An inductance will be something that is given to you in a circuit, but the thing that generates the voltage drop across an inductor is a change in the current, because that is attributed to Faraday's law. Let's go through an example on computing inductance, and this is for a solenoid. We first find the flux, which is mu naught times little n times I times A, which is the area of the loop. Recall last week that mu naught n I is the magnetic field. Then, big N is equal to little n times L, which is the length in consideration. Therefore, multiplying n times phi will give you little n squared. I'm going to divide L onto the other side to get inductance per length, and I'm going to divide out the current, as that is part of the formula, and this gives me the inductance per unit length as mu naught n squared times the area. This is an inductance per unit length. In your homework, n can be figured out from the geometry, and you will need to integrate. In your homework, you have a torus, and you want to find the self-inductance of a torus. The total n can be found by the radius, which is 2 pi a, divided by the diameter of the cross-section between them, which is about d. And then you can figure out by integrating instead of just multiplying in an area, because if you recall, the torus actually does depend on r. The difficult part here might be finding the differential area, and we've done a similar integral in the previous example, so you should try and follow that closely to guide in your homework. As a quick note on number 1 as well, it follows very closely to examples number 1 and 2. So hopefully with those two examples, you will see exactly how the velocity shows up in homework number 1 and how to follow the exact steps to do so. As a final note, we will recall superposition, which is important for the third homework problem. We have a sphere with a cavity. Recall earlier that we found the electric field of a ring by taking an electric field of a bigger disk and subtracting the smaller disk. The same situation happens here. You have a cavity in a sphere, which can be thought of as a big sphere minus a little sphere within it. This is an instance of linearity, or the principle of superposition, as you might remember. The separation vector moves the center to this big R that you're given in the problem. Therefore, you would need to figure out a way in which to find the electric field from a sphere that is off-center. Since it is off-center, you need to change that radius vector to r minus r, to note that you're shifting the origin for the electric field coming from the smaller sphere. This will hopefully aid you in solving the specifics of the problem. Thank you for coming to the recitation today, and I will see you next week.